let's move on to the next speaker today, which is Trygve Leithe Svalheim. Trygve is a PhD student in Oslo, and he will be talking about polarized foregrounds. So Trygve, please go ahead and share your presentation.
So I'm back, and this time I will be talking about polarized foregrounds. My name is Trygve Leithe Svalheim, and as you heard, I'm a PhD student in Oslo. This is the work that appeared on the archive from my paper on Wednesday. So if you're intrigued by what you see here, go have a look. So first, the overall motivation of this is, as you might have heard, finding the primordial gravitational waves. And the reason we're interested in foregrounds is evident when we look at what a B-mode signal looks like for a optimistic prediction of R equals 0.01, a tensor to scalar ratio here. And if we look at the amplitudes of this map, that's 0.1 micro K. And if we now look at the LFI sky as seen by the 30, 44, and 70 gigahertz in polarization, we see that the amplitude is 30 microkelvin. And this signal is mainly foregrounds. So we definitely need to know those to great precision. And you've seen this data model probably a few times now. I've left out some noise terms here, but for this particular work, we're interested in this mixing matrix here, which carries these beta values and the amplitude for each foreground component, which we see here, the visualization of. And that's what translates the foreground behavior in frequency. And our explicit model for this in BeyondPlanck is these three components for polarization. It's the synchrotron, where we model it using a power law without the curvature term this time, and a modified blackbody, where we have a free parameter beta for the tail of the distribution, and also a temperature, which we fix because of the lack of any very high frequency observations in polarization. So as you've also might have heard, we are sampling a vast amount of free parameters, and to sample this directly from a posterior distribution is simply unfeasible. So we resort to Bayesian component separation through the commander framework. And this works by dividing our posterior into these conditional distributions and sampling each of the instrumental and systematic foregrounds at the same time. We're sampling them jointly, not at the same time. But new to this is now including the gain and the correlated noise and the bandpass corrections in addition to the foreground components, amplitude and spectral indices. And this work here is focusing on the A and beta. So the first of the two conditional distributions that we focus on is the amplitude distribution. And just to get a quick overview of this, we define this vector M, which consists of all the sky maps, where A here, capital A, is the beam and the mixing matrix, which includes the beta spectral indices and the amplitude A and some Gaussian noise term. And if we assume that this is Gaussian noise, we can show that through Bayes' rule that this is the distribution that we would like to sample from. And we also see that this is in fact a multivariate Gaussian. And from doing the math here, I won't show you that, but if you're interested, you can look it up. It's explicitly derived in the BeyondPlanck 01 paper. We see that we can draw a sample by solving for A here. And we do this using a conjugate gradient solver within Commander. The next step is the spectral index sampling. And it takes a similar form, but this time around we're interested in the beta term which was in the mixing matrix within A. And because of the nonlinear relationship here between beta and the data D, we can't use a simple CG solver as we did previously, but have to resort to a Metropolis sampler instead. And this takes a bit longer, but as you know, probably is a Metropolis sampler works like drawing a proposal for beta change in the spectral index, projecting that to map space in our case, and assessing the goodness of fit before accepting or rejecting that change. And we do this for several times within one Gibbs iteration. So we must explicitly talk about the data included in our model when we talk about our spectral index results, because as you know, this is our data set. It's the LFI time order data. Oops, it started lagging quite a bit now. So yeah, so the we include the LFI the three bands in time ordered in time domain, and in addition to that, we also include the 353 channel to get an estimate of the thermal dust component, and we also include 3 WMAP bands. And what's new for this study in particular is the use of full covariance matrices for WMAP. And that means that we actually get an improved ability to identify noise on a band-to-band basis. And this is explicitly powerful because the WMAP systematics are contained to the WMAP data. So that also means that we have to downsample our data, so we run it at n-side 16 instead, or these covariance matrices would be extremely large. So in addition to this, we see that both the K band here and the W band is actually left out, and the K band is simply left out because it's a very, very good measure of the synchrotron component, but the amplitude is simply too high and would overshadow any results that we would get from the LFI data. And I again emphasize that the LFI analysis is our main focus here. The WMAP band is also left out, and that's because of known systematics in that data set. So overall, you can see that in comparison to what has been done previously in similar studies or what is possible, this is quite a sparse data set, especially because we're leaving out these intermediate Planck bands here. And we therefore emphasize this is a showcase of the algorithm, to show how powerful a full joint analysis can be, and not necessarily aiming to put very strong constraints on any particular parameter. So spectral index spatial variations is an interesting thing when dealing with foreground studies, and in particular in doing this, we again emphasize that our data set is quite sparse, and we would in principle like to sample these spectral variations or these spectral indices per pixel in the highest possible resolution, but our data set doesn't allow that. So for the synchrotron component, we actually divide the sky into these large areas that we sample independently instead. For the thermal dust component, the thermal dust beta, we sample that on a full sky. And again, we don't have those intermediate Planck bands that could potentially constrain that even better, but again, showcase of the algorithm. So, results. For you to actually trust our results, it's important that we show you our goodness of fit first. And the residual maps per frequency is a good way of doing this, where we see the data minus our model and how we and our final results. And this is the 30, 44, 70, and 353 frequency bands. And overall, they look very nice. There's very little excess signal here. Some small stuff along the galactic plane, but overall looking very good. The 44 gigahertz is standing out with quite a bit more amplitude here. And we also emphasize that this is a plus minus 3 microkelvin, so quite little. But this is actually because of the known excess noise that is described in the noise presentations previously. And in addition to this, these all act as reference bands for the 3 different components. And that also means that some of the noise will seep into the synchrotron or the CMB component. So this 353 channel in particular has very little signal, and that's because it serves as the reference for thermal dust and doesn't have any neighboring intermediate Planck bands, which means that this almost deterministically sets the thermal dust component, and therefore whatever stuff is in here goes into the thermal dust component, and that's something that would be solved by including more data. But again, thermal dust isn't our focus here. So again, over to WMAP residuals. And here, in comparison to the other ones, we definitely do see some large-scale systematic structure, something that doesn't look astrophysical in origin. And the good thing about this is that we immediately actually recognize this pattern. And this is something that has been reported by the WMAP team as through these imbalance templates, where they actually have measurements of poorly measured modes that they predicted, and uncertainties regarding these that are still in the maps. However, because we actually apply our covariance matrices in our analysis, this doesn't propagate into our final results in any way. So that is a good thing. So over to the dust amplitude. Again, this is almost deterministically set by the 353 channel, but the maps are pretty nonetheless. And we see here an animation over 200 samples where the noise fluctuates over the full sky, but there's almost no change along the galactic plane. Next, the synchrotron component, where we see a lot more fluctuations, and this is all due to the full workings of the BeyondPlanck algorithm. And this also includes the burn-in phase. So if you look closely around the galactic plane here, you can see that it starts off being quite bright and then dims slightly before settling in after the burn-in phase. And that shows even better how these fluctuations in the galactic plane that we see in these standard deviation maps here resemble temperature to polarization leakage that could be because of the fluctuations in the bandpass modeling that we apply. But overall, no large-scale systematic stuff that's uncomfortable. And to validate that, we look over at the differences with the K-band for WMAP, which we didn't include. And we see this dipolar structure here, and also emphasize that the differences that we see here are on the order of have an amplitude of 10 microkelvin. And these are too big to be fully explained by spectral index sampling. So there's, unless those are crazy large and not as reported by the literature. So this is definitely something that has to do with another part of the analysis. Differences in regards to N-type. We see overall the structure is there. It's quite similar And there are uncertainties in the time-dependent gain model adopted by NPipe and BeyondPlanck, and that's actually been reported and is well understood by Gjerløv et al. 2020 and other yeah. So a lot of this morphology that we see here is actually well understood, but overall it agrees quite well. So over to spectral indices and its variations. So first off, we, as I described earlier, we did split the sky into these disjoint regions, and we tried quite a bit of different variations doing this. One of these was using 9 regions and applying a prior of -2.8 for every region. And immediately we see a large outlier here. The galactic center prefers a value of -4, which is a lot larger than what is reported in other literature. And that could very well be a coupling with systematic effects such as temperature to polarization leakage around this complicated area of the sky. And there's also some in the Gum Nebula and these areas close to the galactic plane that has little signal overall. In addition, because we apply this prior, we see that some of these low signal areas do actually tend to go towards this value. And these bottom left values actually has been seen in our studies to go even lower and to be degenerate with other parts of the sampling steps, such as gain or the correlated noise sampling. And so this is the final setup that we went with, the 4 disjoint regions. However, even doing this, the high latitudes here and the galactic plane were degenerate with some of the other procedures. So we instead sample these directly from the prior, which means that we don't necessarily gain anything explicitly from the data and focus on these 2 regions instead, what we call the spur and the galactic plane regions. And the final results here are that they seem to be data driven and converge on these 2 values. And from these and their width, we can't deduce any significant spatial variations. And one last thing that is I think the coolest thing about this analysis is this plot here. So if you haven't been paying attention until now, this is the time to do so. This plot here on the top right shows a validation run. It's 3 different runs of Commander with 3 different setups. So this histogram here, the solid one, that's the main one that we reported. All of these are for the spur region. And this is with a prior of -3.1. And the red lines correspond to the prior of -2.8. But the dashed lines represent Commander runs where we don't marginalize over the TOD parameters. So in both of these, the TOD parameters are fixed at some set of TOD parameters, where in the solid ones, we explore the full TOD parameter space. And this is really cool because when you look at the width of the full TOD run, we see that it's almost double the blue dashed line. But it does also include this area where it's really exploring the full parameter space. And with this red one with a different prior, we do also see that it gets pulled towards the -2.8, but it still stays within reasonable values. So finally, we also did look at the dust spectral index, and these are the final results for that, applying a prior of 1.56, which is reported by the Planck collaboration. So it's within healthy values, but it's slightly steeper. And that might be because of a steepening in the dust beta parameter, which has actually similar stuff has been seen in temperature analysis before. But this definitely warrants further investigation, and maybe this is a result of too simple bandpass correction. So in summary, we have constraints on synchrotron and dust polarized spectral indices. We find no evidence towards spatial variations in the sampled regions, which is a good thing for future analysis, if that's true. And this is the first joint sampling of amplitudes and spectral indices to combine LFI and time domain with low resolution doubly mapped data. So that is nice. And this plot shows how the results ended up describing the full polarized sky with a spinning dust of 1%, which is put in there artificially and not something we deduced. And this also shows these extra bands that could potentially be implemented in the future. So thank you for the funding. And are there any questions?
Thank you, Trygve.